want the function to do. For example, deleting data. Here, we'll delete data from the table, and then we'll scan and print it again. Now, if we execute this, you can see that I start out by scanning the table and the data's there. But then the items get deleted, and afterwards, there's nothing in the table when we scan and print it again. Let's assume this is bad for this use case, and that we don't want this function to be able to delete data for whatever reason, only to read it. So, what we need to do is update the IAM policy statement here. And instead of giving it permission to do any action, let's restrict it to a set of read-only DynamoDB actions. Again, on any resource in the account. Now, this is an improvement because now I only have read access. So let's restore our database contents and try again. This time, we can see that the read works fine. But if I try the delete again and scan and print, we'll see that this won't work because the function doesn't have permissions to delete from the table anymore. Here you can see the error, saying that the delete item operation for this particular role was not authorized to perform a DynamoDB delete item action on the particular resource that it points to, this table. So that's an improvement, but we still have a big security hole. What if I change this to try reading from a different table? Say, some corporate financials from a totally different app in the account. This function certainly should not be able to access it. Now this actually worked. As you can see here, it was able to read data from the other table. The reason is because this function's IAM policy allowed it to access any resource in the account, which means any DynamoDB table. So let's update this to only allow it to access the My Demo App table and the indexes associated with that table. After this change, if we try again, we'll see some different results. Now, when I try to look at the corporate financials table, I get an error saying that the Lambda's role is not authorized to perform a scan operation on this other table. But of course, I can still read from the table that I intended to read from. There's my data, still accessible. Next, we'll continue on and learn how to keep your data secure using the AWS Key Management Service. Encryption can feel like a complex and daunting area to work with. But in fact, AWS's Key Management Service, or KMS for short, is actually very straightforward to work with. If you understand KMS, you can keep your data secure at rest without having to delve into the complexities of crypto yourself. To start using KMS, you need to know how to use an AWS KMS key, how AWS services integrate with KMS, and how to use IAM to control access to the KMS keys. So let's look at this now. But before I show you the next slide, I want you to know that it's 100% okay if you don't understand everything you see there. And I'll explain why that's okay in just a moment. But hey, since this is a session for builders, I do want to take just a moment to explain the basics of how KMS works. If you have small amounts of data you'd like to encrypt or decrypt, you can simply use the kms.encrypt and kms.decrypt API calls. These APIs will let you encrypt and decrypt data yourself as long as the chunks of data are up to 4 kilobytes in size. But you also don't need to do this at all, even for small chunks of data. For example, if you're using Amazon S3, our simple storage service, to keep some data, and you want to encrypt it, you don't need to encrypt it yourself in 4 kilobyte chunks. Instead, KMS tightly integrates with many AWS services, including Amazon S3, to make this process much easier using something called envelope encryption. The way this works is that KMS first generates a symmetric encryption key. Then, it cycles through your data in 4 kilobyte chunks and encrypts it. Then it encrypts the symmetric encryption key with the KMS managed key. And finally, it stores the encrypted symmetric key alongside the encrypted data. When it needs to decrypt the data, it first decrypts the symmetric key and then uses that key to decrypt all of the encrypted data for you. Now, the reason why you didn't need to understand all of this is because many AWS services will manage all of these KMS mechanics for you. And this is the way you'll probably interact with KMS. Here's one service integration example to look at. Here, I'm creating a new Amazon S3 bucket to store some data. And of course, as a matter of good security practices, I'd like this data to be encrypted. Now, I have two choices. I can select the first option and allow Amazon S3 to manage its own encryption key automatically, or I can specify a KMS key that I've created from the KMS service. Let's assume I've already created a KMS key and that I want to use that option here for encrypting my data in this bucket. There are some nice advantages to using KMS instead of letting Amazon S3 manage the key itself, because it means I have more control over who can access the key, and that access can be logged too. And so, assuming I've set up my S3 bucket to use a specific KMS key I created, what happens when someone tries to access data in the bucket? Well, let's assume that the identity accessing the data has this policy associated with it. What happens? Do you think this policy is enough? Well, it turns out that no, it's not enough. While this policy does grant access to the objects in the bucket, if those objects were encrypted with KMS, then they won't come back from S3 unless the user has permission to have S3 use the KMS key to decrypt that data. Instead, this is the additional statement we need to add to our policy to allow the identity to access the encrypted data in the bucket. We need to add an explicit set of actions related to encryption and decryption, and we need to specify our specific KMS key that's being used for the bucket in question. See? With KMS, you get tight control over the key used to encrypt data and the identities that are allowed to access that key. And now you know all the basics of using KMS to keep your data protected at rest. And finally, let's explore the third aspect in our trio of security-related services. It's time to talk about network security and the concept of a VPC, or Virtual Private Cloud. As a builder, if you've only explored AWS's serverless offerings, it's possible that you may not have encountered the concept of a VPC yet. But the odds are, sooner or later, you'll find yourself needing to isolate some of your cloud resources onto their own logically segregated, software-defined private network, or VPC. And when that day comes, you'll need to know how to keep the resources in your VPC secure. So at a minimum, you'll need to understand the core concepts behind our networking security concepts of subnets and security groups. And you'll also want to understand how network routing happens inside of a VPC, and your options for keeping some of that routing private. So that's what I'm going to teach you about now. Firstly, let's talk about what a VPC is exactly and what goes in it. An Amazon VPC lets you provision a logically isolated section of the AWS cloud where you can launch AWS resources in a virtual network that you define. You have complete control over your virtual networking environment, including selection of your own IP address range, creation of subnets, and configuration of route tables and network gateways. You can use both IPv4 and IPv6 in your VPC for secure and easy access to your resources and applications. You can easily customize the network configuration of your Amazon VPC. For example, you can create a public-facing subnet for your web servers that have access to the internet. You can also place your backend systems, such as databases or application servers, in a private-facing subnet with no internet access. And you can use multiple layers of security, including security groups and network access control lists, to help control access to Amazon EC2 instances in each subnet. So let's explore this in more detail. First, AWS has many regions all around the world. And each region in AWS is comprised of data centers that make up what we call availability zones. Well, every VPC you create lives inside a specific AWS region. And when you define a VPC, you specify a range of IP addresses that you want the VPC to be responsible for managing. And inside a VPC, you portion off part of that network into subnets that are each associated with a specific availability zone in that region. You can see in this example, we've created a public and a private subnet in several availability zones for this VPC. And each of these subnets gets allocated a different portion of the VPC's IP address space. So, these subnets live in an availability zone, and each of them gives us a place where we can launch AWS infrastructure. So let's deploy some services into this network. In this example, we'll deploy a very simple web application consisting of a bunch of application servers that sit behind a load balancer. Now, I really just created one instance of AWS's application load balancer, but when I created it, I specified that I wanted it to operate in each of my subnets. So you can see it reflected here accordingly. And in each of my public subnets, I have an application load balancer, and in each private subnet, I have a collection of EC2 instances to serve my application. What I want is for all of my customers to be able to talk to my application load balancer so they can interact with my web app. And I want to ensure that only the load balancer can interact with my application servers themselves. I do not want any way for devices on the public internet to be able to communicate directly with these application servers. As part of this, a common scenario for web apps is that you'll have a database that the application servers talk to. So I'm showing that here with the Amazon Relational Database Service, or RDS, icons. Let's say I have an RDS primary server in the private subnet of one availability zone and a failover read replica sitting in a different AZ. So now, let's talk about how we can keep this network secure. If you understand nothing else about VPC networking, I hope you will at least understand this concept of security groups. A security group acts as a virtual firewall for a virtual machine instance running in your VPC, controlling its inbound and outbound traffic. And these security groups are a very useful construct to control access between the different parts of the VPC. As you can see here in our example application, we have three clear groups of resources: the load balancer, the app servers, and the database servers. And each of these groups has very different rules for the kind of traffic it's expecting to handle. We implement these rules inside of our security groups. You can choose to associate the resources in your VPC with security groups. And each of these security groups can have a number of rules in it governing the inbound and outbound traffic that it will permit. So here are some screenshots from the VPC console. Of course, you can also specify all of this via the CLI or via infrastructure as code tooling. But the concepts are easiest to see here through the console UI screenshots. Firstly, let's look at our load balancers. Their job is to listen to HTTPS traffic from the public internet. So the security group that they belong to needs to allow traffic in on port 443. And it should permit this traffic from anywhere on the internet, which we show with the 0.0.0.0/0 notation here. And this is the only rule I need here. I don't want traffic to be allowed into the load balancer on any other ports. And if I don't have a rule allowing it, it will be implicitly denied. These security groups are stateful firewalls. They just govern the initial connection. If an incoming connection is allowed, the firewall will keep track of that connection to make sure that the response data gets sent back through without an issue. So that's the application load balancer, allowing traffic in on port 443. Next are the web application servers. They are definitely expecting to be able to serve traffic requested by the load balancer. In this case, I have the application servers listening on port 8443. So in the security group that they belong to, I'll add an inbound rule allowing TCP traffic on that port. And instead of specifying an IP address for the source of this traffic, I can use another very helpful feature of security groups and specify the ID of the application load balancer security group instead. That means that any of my application load balancer instances, regardless of which AZ they are in with their various IP addresses, will be allowed to send traffic to my web servers. Finally, I have the databases in their own security group as well. And this security group is configured to only allow incoming traffic for a MySQL database on port 3306, and only if the source of the traffic comes from the security group containing my web app servers, since those are the only machines that need access to the database. So that's how all this works. It's actually pretty simple. You group your VPC resources together into security groups, and for each group, you specify the ports and sources for traffic they should be allowed to receive from or send to. That's it. So, that's it about security groups, but we can improve our security posture even further by configuring the traffic routing rules for these subnets. So far, I've just called them public and private, but we haven't yet examined what makes them so. It would be great if we could, for example, declare that the machines in our private subnets will not have a network route to the public internet. In fact, at AWS, this is what we mean when we call it a private subnet. So, each subnet in a VPC has a route table. And here's the most simple route table that there is. It has only the one default route, which says basically, packets that are destined for machines in my VPC should get routed. There are no routes for packets to hosts outside of my VPC. Now, if we go look at the route table for these public subnets, we have a different story. Our public subnets have application load balancers, and these are going to need to be able to receive traffic from the internet and respond to it. So, we do this with an abstraction called an internet gateway. It's a robust networking construct that gives us a way to route traffic from and to the internet. Here, we have the same default rule that routes all traffic inside the VPC, but we have a second rule saying that for any other IP address, here represented by 0.0.0.0/0, the traffic should route to an internet gateway resource that we've created in our VPC. Now, there's another pretty common scenario that I'm not going to show here, but I'll just talk about it for a moment. Sometimes you may have resources in private subnets that you definitely don't want to be addressable from the internet, but you may want to grant them the ability to communicate out to the internet. So, in these cases, we have another abstraction called a NAT gateway, and you can add one of those to your VPC and route to that accordingly if you have that specific need as well. So, sticking with the concept of a local private subnet for a bit, there's one last concept I want to cover. As you use AWS, you'll notice that many of our services, perhaps most, do not exist inside a VPC. For example, when you create an Amazon S3 bucket, or a DynamoDB table, or an Amazon API gateway, or many other resources, you are not asked to specify a VPC as part of your resource creation. And you can also see this if you look at the DNS name for a service's API endpoint and resolve its IP address. For example, if we look up Amazon CloudWatch's IP, it resolves to a public IP address. This is not an address in our VPC. So the question you may be asking at this point is, wait, I want the ability to keep resources on my private subnet from talking to the internet, but I also want the ability for them to communicate with these other great AWS services. So how can I do that? For example, you might have EC2 instances running in your private subnets, and you may want to run the CloudWatch logs agent on these instances to ship their local log files up to the CloudWatch logs service, so you have a central place to aggregate and search through all of your logs. The only problem here is that CloudWatch isn't in our VPC. So how do we do it? It turns out that the solution here is something called a VPC endpoint. Many of our services allow you to create a VPC endpoint for them. And what you end up with when you do so is an IP address inside each of your VPC private subnets that you can use to communicate with the service in question. And if you use these VPC endpoints, the DNS name will also get configured for you. So your code can continue to talk to the DNS names the same as before, but now the traffic will get routed appropriately through the VPC endpoint. Finally, bringing this full circle, one additional benefit of VPC endpoints is that they give you the ability to use your VPC identifier inside your IAM policies. For example, if you use an Amazon S3 VPC endpoint, you can attach a policy to a role stating that it only has permissions to access a particular S3 bucket only if the network path matches the VPC that we want to ensure the traffic is coming from. This is a really powerful security capability, since it effectively restricts the usage of this role to access our S3 resource from inside this network. If another identity tried to use this role to launch an EC2 instance from another network to try and gain access to the data in this S3 bucket, it wouldn't work because this policy wouldn't be satisfied. Congratulations, you made it to the end. And now you have a foundational level of understanding for what's involved in keeping your resources secure on AWS. We talked about permissions management, about who you are and what you're allowed to do in AWS. We talked a bit about encryption. If you want to encrypt data at rest, look for the KMS integration to give you easy and powerful control over the keys and encrypt your data. And you learned about how to take control of these features in VPCs to increase the security of your networks. I want to just end with a reminder that security in the cloud is a shared responsibility. Remember that AWS takes care of security of the cloud, and as a customer, it's your job to manage the security of the workloads that you run in the cloud. These tips and concepts you learned here today will serve you well on your path towards increasing the security of your work in the cloud. Ready to build? AWS Digital Training offers free, on-demand digital courses that help you learn new cloud skills and services when and where it's convenient for you. Register for free AWS Digital Training at aws.training. Thanks for your time. We hope you found this interesting, and I request you please complete the survey before signing off. Let us know what you thought of today's event and how we can help improve the event experience for you and others in the future. And finally, I just want to say thank you for taking the time to let me share this session with you today. I know your time is valuable, and it means a lot to me that you stayed with me until the end. If you have any questions or comments that you'd like to share about today's session, please just get in touch. You can find me on LinkedIn and Twitter at Gabe Hollenby. Thanks again.